Hello students, welcome all. So we are going to discuss today about the application of trigonometry. So trigonometry, you may think that where it is getting used. It is applied in almost all the chapters in almost all the concepts. So let us try to see a new perspective of its application in almost all the concepts of physics. So I will try to give as many applications as possible, some of which you will start seeing it from the current chapters only, but some of this you will be seeing afterwards. But let us start this. Okay, let us start this. Application of trigonometry. Remember, we have covered all the important concepts of trigonometry. So now we are seeing applications of trigonometry. Trigonometry applications. So let us start with the first application, which is called resolution. Which is called resolution of vector. Resolution of vectors. Resolution of vectors, or resolution of a vector, into two perpendicular components. Two perpendicular components. Okay. So suppose, let's start with an example of a force vector. There is a force vector and there is a single vector, and I want to break this force into two vectors. But those two vectors has to be perpendicular vectors. Okay, that is where it is important to understand. Suppose that there is a force vector, its magnitude is F, okay, and its direction is shown. Let us first of all consider direction means angle with x-axis. So if I assume that this is x-axis, then that's the angle theta. Okay, so this force is having magnitude. Magnitude means it is the length of this line. A vector is represented by magnitude and direction. So magnitude is represented by the length of this line, that is F, and angle is represented as angle from the x-axis, positive x-axis. Okay. Right. So now I want to break this into two components. See, if I want to break it into two components, I want to break it one component along x, which is called fx, and one component along y, that is called fy. Okay. So the component along x is fx, and note that they are going to be perpendicular because one is along x-axis, another is along y-axis, and this is also called triangle rule. Triangle law or triangle rule is used to add two vectors. So this is one vector and this is another vector. So this plus this is giving us this. Okay, that is called triangle rule. It's not necessary that it has to be right triangle. It can be any kind of triangle, right? But here we are taking this as a right triangle. Why? Because adding this fx and fy means they are along x and y axis, so definitely they are perpendicular. That's why we are calling them as perpendicular components. So sum of fx and fy vectorally, if I write vectorally, then I will write fx vector plus fy vector. These two vector is a vector. Okay, it is it is not just the sum of these two, magnitude. It is the vector sum. This is vector sum. So sum of this plus this is giving us this. Okay, and this it is valid in any kind of any two vectors can be added to the resultant vector. For example, suppose if I say this is one vector and this is another vector, let's say this is a vector and this is b vector, then according to triangle rule we have to add them and give them like this way. This is the resultant vector, which is the sum of a vector and b vector. So if I represent the length of this line as a, this length of this line is a, the length of this line as b, and the length of this line as capital R, then there are relationship between them, right, that we can see. But note here we are focusing on only perpendicular components, right? So this is the first component fx and this is the second component fy, and we can also show them as a triangle as well as parallelogram. So I can also represent them as a parallelogram either. Okay. So I can represent them as a parallelogram also. So suppose I draw parallelogram, then this is my y-axis, right, and this is my x-axis. So I can also represent this fy like this way also, because we can slide it parallel to this. So if I focus on drawing parallelogram, then I will consider this as first factor, this as second factor, and then I will join this the diagonal. The diagonal will be like this. Okay. So you have to make a parallelogram, then in that case, then you can. So parallelogram law, triangle law, they are not different. They are almost giving the same result, right? Because the third side of the parallelogram, which is the diagonal here, is the diagonal of the parallelogram. The third side of this triangle is the diagonal of the parallelogram. So basically, they are the same thing, but direction you do clearly. Okay, in a parallelogram, this is like the common tail. The tails are common, and this is the diagonal. And if you are taking the triangle now, then the head of the first is joining the tail of the second, and then you're joining the uh, tail of the first with the head of the second. So this thing should be clear. Okay, right? So why are we seeing trigonometry? This is vector, right? But no, trigonometry it is not vector, because see here, this line is f, this line is fx, this line is fy, this is 90 degree, this is the, isn't it a right triangle? Isn't it right triangle? Can we not apply sine cos? Apply sine cos. What is cos theta? Cos theta is base by hypotenuse, so fx by f, so fx become f cos theta. Very important. Similarly, sine theta you apply, sine theta is fy by f, so fy becomes f sine theta. Very important it is, very ultra important it is. So a force which is in this direction can be resolved into two perpendicular direction. You know, direction I am showing only the magnitude here. Direction you can show definitely. Suppose if I have to show direction, so I will show direction of this like this, and direction of this like this, and direction of this like this, right? I can show it like this. But definitely here I am talking about the magnitude. So magnitude can be calculated like this. So that means a force can be resolved into two perpendicular components. One is along one direction, other is perpendicular to that directions, right? They are called perpendicular components, right? That's the important thing. Now let's see. A lot of applications are there. Let us try to do that. Okay. And also note that in this case, very important thing is that this f is nothing but fx square f square, or f is the hypotenuse root under fx square plus fy square, right? That means the resultant resultant magnitude is equal to root under fx square plus f, because resultant is the diagonal of this rectangle, which is a of course it's a right triangle, so we can use that. If it is not right triangle, we can think of making it into a right triangle. Definitely we can do that. We'll see it. Okay, so let us try to do further about this. Let us take some example. Suppose this is a force of 10 Newton, and I want to break it into two directions. One, and these two are perpendicular directions. Note that I want to break it into two directions. So this direction, this force and this force. Okay, they are perpendicular, and of course parallelogram when you draw, you can make it like this. Okay. Note that they have given that this angle is, let us say, 37 degrees. So what will be this component? This component, you will directly say this side it is making theta. This will be tan cos 37 degree, and this is tan sine 37 degree. So sine 37 is how much? 3 by 5. So this will become how much? Tan into 3 by 5. So it will become 6 Newton. Similarly here, cos 37 is 4 by 5. This will become 8 Newton. Okay. So whichever side angle is there, we can resolve. This is full of trigonometry, complete trigonometry it is. Okay. So of course, we know standard direction is x and y, so we can resolve along standard direction anything. So let us try to add forces. This is resolution, by the way, we can resolve it. And suppose I want to add forces. Let us take the example of adding forces. So one force is on a body, there is a force of 10 Newton acting in this direction from horizontally 37 degree. Another force is 10 Newton acting vertically. Another force 10 Newton acting in this way. It is making an angle of 37 degree like this. Okay, and one 5 Newton acting like this. And they ask what is the total force? What is the total force acting on the body? They ask suppose. So how to do that? Let us break all the forces along x, y, along x, y, along x, y, right? So one is x, one is y. Let us see that how to do that. So this is the first force. Let us break this first force here. So this becomes 10 cos 37 and this becomes 10 sine 37. Similarly, let us break this force, which is 10 cos 37 and here 10 sine 37. All others are vertical only. So let us now write all the vertical forces and horizontal forces. Note that this 10 cos 37 and cos 37 they are equal, so they are going to cancel out. So in the vertical direction, we are going to get tan plus 10 sine 37. 10 sine 37 means 2 times 10 sine 37, right? And this below, this is 5. How much this will give? So this is 20 sine 37, 3 by 5. Calculate 5 into 4, so 12. This will become 22, right? So now 22 is larger than 5, so net force will become opposite, means you will subtract 22 minus 5, that means 17 Newton. So the total force acting on the body is 17 Newton. This is what is the application. So you can see, you can do it anyway, right? It's quite easy to do that. You can resolve all the forces along x-axis, along y-axis, and find the resultant force along x-axis, net force along x-axis, then calculate net force along y-axis. They may be positive, negative, we do not know. But after calculating this, you can draw this and make this rectangle, which is the net force. So this net force is root under net force along x-axis square plus net force along y-axis square. Like this you can do it. And suppose they ask what is the angle the resultant is making. So this angle theta we can definitely calculate, right? So how do we calculate this angle theta? This angle tan. Now again trigonometry. Tan theta. Calculate tan theta. Tan theta is the net force in y by net force along x. That's all you will calculate tan theta, right? This is all full of trigonometry. So we can apply this trigonometry in the vector calculation, in the vector resolution, in the vector addition. All this we can apply, right? All this we can apply and we can do that. So that's one application. Now let us go into the second application, which is called Lami's theorem, or which is also known as sine rule. Second application is called sine rule or Lami's theorem. Lami's theorem. Okay. So suppose there is a body on which three forces are acting: F1, F2, F3. Okay. These forces are concurrent, or we want to make them concurrent, and opposite to F1 is angle alpha, opposite to F2 is beta, opposite to F3 is gamma. Okay. Sure. I can draw them as a triangle also. Suppose I draw this as f1. This is f1 vector, right? Where is my f2 vector? F2 vector is this way, okay? So I am drawing this f2 vector, right? And then I am drawing f3. F3 is coming like this way. So let us draw this f3 like this way. Okay? F3. Note that I am considering equilibrium. That means sum of f1 vector plus f2 vector plus f3 vector. Sum of all these three vectors is 0. Right? Technically, sum of all this is 0 means null vector. Now this is the same diagram I have shown by translating. A vector can be slided parallel to itself, right? So this f1 I have slided this here. This f2 I have slided here. This f3 I have slided here. So sum of these three is 0 means it has started here and it will come back to the same point. So if you, let us say it is like displacement, so it starts here and coming back here means total displacement is 0, right? Distance may be there, but displacement will be 0 because you start from your home and come back to your home. Displacement. So same thing. Displacement is 0 means like a vector addition. So force addition total is coming back to same point means it is 0, right? Okay. So equilibrium it is now. Sine rule. What is sine rule? First of all, sine rule. I will mention it. Suppose there is a triangle ABC and opposite of angle is side length A, opposite of angle B is side B, opposite of angle C is side C. So A by sine A is equal to B by sine B is equal to C by sine C. Okay, so that's the rule, right? So similarly here try to find out angles here. So we know angle alpha is between F2 and F3. So this is F2 direction and this is F3. So this angle is alpha. Note that this angle becomes 180 minus alpha. Similarly, beta is between F1 and F3. So F1 is going like this way, F3 direction is going like this way. So this angle is beta. So this becomes 180 minus beta. Similarly, if you see gamma is between F1 and F2. So this is the direction of F1 and this is F2. So this is gamma. So this angle becomes 180 minus gamma. If you apply this rule, if you apply this formula here, immediately you will get this result. Why? Because if I take this length F1, opposite of F1 is 180 minus alpha. So sine 180 minus alpha I will apply. F2, opposite of F2 is 180 minus beta. So sine 180 minus beta I will get. And opposite of F3 is how much? Where is F3? This is 180 minus gamma. So sine of 180 minus gamma is there. So you know now trigonometry sine 180 minus alpha is same as sine alpha. F2 sine 180 minus beta is same as sine beta, and sine 180 minus gamma is sine gamma. You may say how? How sine 180 minus theta is same as sine theta? How sine 180 minus theta is sine theta? So draw the quadrant. Okay. Suppose for example 180 minus theta means what? Suppose for example this is this angle. Let us consider this angle as uh, 180 minus theta. Okay, or you consider this as theta. If you consider this theta, then what is this theta? Because this theta is, let us say, obtuse. Then here what happens? You're going in this triangle. This is how much? 180 minus theta. Then this is 180 minus theta. Correct? Maybe I will write it here. This is 180 minus theta. This angle. So sine of this theta, remember this is perpendicular. Let us say that this x and this is y. But x will be of course negative this side. Y is positive. Hypotenuse is always positive. So this sine theta is going to be same as sine 180 minus theta. 180 minus theta. That's what it is. Okay. Second quadrant sine is positive, right? So that's how it is coming. So this is an important rule and it is used to solve many problems of static equilibrium. Equilibrium whenever is happening, we can apply this concept and we can solve. Let us take one example. Very important example. Suppose that there is a cylinder or sphere also you can take, and this is kept on two inclined plane, right? Two inclined plane. This inclined plane makes angle alpha, this makes angle beta. They are different, and this has got a mass m. So I want to draw free body diagram. So when I draw free body diagram, this is weight mg, right? And note that here there is a contact force between them. So if you have got some idea of normal contact force acts perpendicular to that. So here there is a normal contact force. Let us call that as N1 and this as N2. And now let us draw free body diagram. So first of all, you should know that suppose this is inclined plane of angle theta, the normal to this normal will make same angle with the vertical theta. This concept also we should know because this is 90 degree and this become 90 minus theta and total must be 90 degrees. So this is also theta. So this is the important concept you should know. Angle between the inclined plane and the horizontal is the same angle between the vertical and the normal to the inclined plane. So that means this normal N1 which I have drawn here, I can now draw this diagram here clearly. So this is the weight mg, right? And I will draw this normal N1. Remember, normal will make angle alpha with this, right? Because this is making angle alpha. Similarly, this normal N2 will make the same angle beta like this. So now if this is in equilibrium, I can apply what? I can apply the Lami's theorem. So this angle becomes 180 minus beta and this angle becomes 180 minus alpha. So I can apply N1 by sine of 180 minus beta is equal to N2 by sine of 180 minus alpha is equal to mg by sine of alpha plus beta. So from here we get this N1 by sine beta, right? N2 by sine alpha is mg by sine alpha plus beta. And suppose if we need to calculate N1 and N2, so N1 can be calculated as mg times sine beta by sine alpha plus beta, right? Alpha plus beta. Similarly, we can calculate N2 as mg times sine alpha by sine alpha plus beta. Like this, we will be able to calculate, and this is a simple approach, but this is a very fundamental approach, sine rule, right? We have seen applications of trigonometry here. So, lot of such applications are there, trigonometry in vectors and forces. If you can get this fundamental concept, then you can solve many questions, right? Okay. So you have to keep on working out problems. A lot of problems will be there, and we will be seeing in this. So let us wind up with this today's application. Then we'll continue further in the next class with the next topic. So we have completed trigonometry. Then we will go to coordinate geometry. So next is the coordinate geometry. Important formulas will cover in the next class, and further we will go down. Right. So thank you for your attention. See you in the next class. Bye all.